Today, we're going to talk about batteries. There's a little problem with batteries. And the problem with batteries is going to be even a bigger problem after we name it, because the name that we gave the problem is worse than the problem itself, because it's a stupid name. The EMF, the electromotive force, which is not a force, but a voltage, was named before we knew what voltage was. But EMF just means the thing pushing the electrons, which is really a voltage, right, and not like a force so much, although there are forces involved. The EMF is the voltage of the battery, which sounds like a dumb thing to say. Why don't we just call it voltage if we're going to call it EMF? And we use this little script 3. It's not a 3, it's an E. I was thinking in my mind backwards 3, which is what it looks like. And I said 3. This is a good recording. I'm glad you're listening. All right. So a little script E is the V of the battery. But the reason that we're going to use EMF or electromotive force or script E is that the voltage of the battery is not the voltage of the battery. Because the battery is a big bag of chemicals that can produce a certain amount of voltage. But producing that voltage takes energy. And the electrons, as they go through the battery gaining energy, actually use energy in the battery as they gain it, which is called internal resistance. So the internal resistance of the battery assumes that the battery itself is a resistor in series with the rest of the circuit. And so the voltage supplied by the battery, you have to subtract out the voltage dropped by the battery itself. So if it's a 1.5 volt battery, but it's got some internal resistance that drops 1/10 of a volt, effectively it's only a 1.4 volt battery. And that's the little complication. So the equation that we'll get, or the assumption we're making, is that between the terminals of the battery is both a voltage source and a small resistor. We're just going to make that assumption that it's in there. And notice my little asterisk here. We're going to assume that internal resistance is 0 unless otherwise stated. Like the problem that you get on a test, for example, will state it has internal resistance, and then you have to find it. If it doesn't say that, you can assume it's an ideal battery. But the EMF is the source voltage, the nominal voltage of the battery, without taking into account its internal resistance. Which means that the terminal voltage of the battery can be calculated like this. V, the terminal voltage of the battery, is the EMF, that is to say, like the nominal produced voltage by the battery, minus the internal resistance. Internal resistance is not IR, it's current times the internal resistance, right? But it's IR, so it sounds like that's an abbreviation, but it's like not, it's a fake abbreviation. So you take the full EMF of the battery, subtract out the voltage dropped by the internal resistance of the battery, and that's going to give you what we call the terminal voltage. Okay, and that is the voltage from terminal to terminal of the battery, what it can actually do. This equation, V equals script E minus IR internal, is a good equation to add to your equation sheet. Or, for the 8th time this year, you can reprint the new updated version, if you'd like, because it's now correct, because it's another one that I forgot. Next year, man, those guys are going to have it easy. All right. So, again, what we care about is this idea of a terminal voltage, the voltage from terminal to terminal, A to B, including the internal resistance of the battery. That is actually going to change. Right, if you have a 10-volt battery with 1 ohm of internal resistance and you connect it to a 1 ohm resistor, how much voltage does your battery drop? You have a 10-volt battery, you got an ohm of internal resistance and an ohm of external resistance. That internal resistance drops half your voltage. Right? 1 ohm, 1 ohm. It's going to share between the two 1 ohm resistors. It's going to share evenly. 5 volts gets dropped here, 5 volts gets dropped there. If you have a 100 ohm external resistor with a 1 ohm internal resistor, then the voltage outside is 100 times bigger than the voltage inside. So the size of the external resistor actually changes how much your terminal voltage is. because the internal resistance of the battery will drop voltage proportional to the rest of the resistance in the system. So the battery's size and strength depends upon what it's connected to because of its own internal resistance. All right. So let's see if we can figure some stuff out. I'm going to take a battery, which is everything between points A and B down here, which is including a 12-volt voltage source and a half-ohm internal resistor. We're just going to pretend like it's a resistor. It's not, but we're going to pretend like there's just one in series there. And I want you to tell me a couple of things. Tell me the total current pushed in the circuit. Tell me the terminal voltage of the battery. That is to say, it's not 12 volts. It's less than that. Tell me what the voltage is of the battery after the battery. And then give me the power dissipated by both the resistor R and the internal resistance of the battery. Tell me how much voltage, how much power is dissipated by each. Okay. Ready, go. To find the total current in the system, we need to remember that we do not have just one resistor, but two. So we're going to say that the voltage dropped across the circuit is 12 volts, but we're dropping it over 65 and a half ohms because we're putting that in series with the half ohm resistor in the battery, which it's not like a little resistor in the battery. It's the equivalent of a perfect battery with a little half ohm resistor. And we're just going to say whatever's going on in there, it's like it's a half ohm resistor. So it's 0.183 amps, not 12 over 65, because that would assume that there was no internal resistance, but there is. So we're going to get a little slower current. It's 0.183 amps. And then if I want to find the terminal voltage of the battery, I use that equation that we just talked about. I say, hey, 12 is my EMF, and I'm going to subtract out of that the internal resistance of the battery, which is the current through the battery, 0.183, times the resistance of the battery. All of this ends up being about 0.1. It's a tenth of a volt dropped by the battery itself, which means the terminal voltage is 11.9. Now, if we have a smaller resistor, if the two resistors get closer in size, if either internal resistance gets bigger or the external resistance gets smaller so that proportionally they're closer together, then the terminal voltage changes, even though the EMF stays the same, because that's just how much it's pushing, regardless of the internal resistance. You with me here? Everybody good? Questions? Cool. Power is V times I, 11.9 volts dropped across the 65 ohm resistor times the current going through that resistor gives me volt amps or watts of 2.18, 2.2 watts. That's a light bulb just giving off 2.2 watts. A watt is a joule per second as much as it's a volt amp. In fact, a volt amp makes a lot of sense that way. It's the question that I took off of the last test because it should have been on the next test and we missed it. But a volt is a joule per coulomb, right? And an amp is a coulomb per second. So what's a volt amp? Joule per second. Hey, it's a joule per second, which we call a watt. Volts times amps is watts. So a joule per coulomb and a coulomb per second gives me a joule per second, which means I get watts of power. So if I'm pushing so many watts, that means that that's how much energy I'm releasing. So if we go back to this problem, 2.2 watts means 2.2 joules released per second. 2.2 joules of energy, of light energy or of heat energy or whatever, per second of time that goes by. That's how much energy I'm releasing into the system. That's how we're going. All right, the battery drops a tenth of a volt at 0.183 amps, which is 0.018 watts, 2/100ths of a joule per second. And that's our little review on power as we learn about EMF and terminal voltage and internal resistance of things. This is how to deal with internal resistance. How are we doing with this? Questions, Josh?
Where did you get 0.1?
0.1 is the voltage drop by, remember, if the terminal voltage is 11.9 with a 12 volt EMF, that means this voltage drop is 0.1.
Oh,
Right? I drop 0.1, I have 11.9 left. You good?
yes.
Okay. All right. Questions? Okay, how about we do this? I have a handout here, a series circuit and a parallel circuit. I'm just going to show both of them. Just imagine that those resistors listed there in the table are in series if you're playing along at home, which none of you are in my class right now, obviously, because you're here. But if you're playing along at home, just draw a series of those. I'm pointing. That's not helping the people who are listening, like pointing. Okay. Anyway, just draw a series of those resistors that you see, and then on the other on the other side of this, let's just to show you so you can do this. Sorry, bear with me, guys. Well, tough. Sorry, can't figure it out. You're going to lose. All right, so we're going to go do this handout, and then we'll be back. Bye. Okay, let's try this again, an explanation. Before you see the answer, person who's listening at home, draw a series with, again, I'm pointing, with the resistors that you see in the table. Just draw them all in series, and then solve the circuit filling in this. Pause it. Are you back now? You should have done it already. If you haven't done it, you're not learning as well as you could be. Oh, geez. Okay, so if I'm solving for resistance, the way I'm going to do this is sum all the resistors together. Right, I just add them all up, and that gives me 25.6 total ohms of resistance in the entire circuit. Yes? Now, I know that I have 64 volts of total voltage dropped across 25.6 ohms of total resistance. So V over R will give me I. That's 2.5. Now, the easy one. Current stays the same in a series. So I can just fill 2.5 all the way down. Are we all okay with that? We all got there? That's just true. If it's 2.5 at the battery, it's 2.5 everywhere because it's just one branch. You can't split. It doesn't speed up or slow down. You have the same amount of electrons going past any part of the circuit at the same time all the time. Then I need to just say I times R is V. So 8 times 2.5 is 20. And 6 times 2.5 is 15. All the way down. And if I want to check if I'm right, what do? Add up voltages A through F, and I get 64. So if I add up all the other voltages other than the total one, I should get 64, and I'm good to go. Now, calculating power, I just multiply V times R, or if you want, I squared R or V squared over R, any combination of those, right? And we get 160 watts, and we do the same thing for each one, and if I add up all of these, A through F, then I'm getting 160 watts, which means that the 6 bulbs are burning with 160 watts, and the whole circuit is a 160 watt circuit. Of course, that's conservation of energy. It can't be anything else. Now, the question I have for you is A through F, which bulb is brightest? Or are they all equally bright? Definitely not equally bright? I want you to talk, just really quick, talk to each other, see if you can come up with a consensus on which bulb is brightest. A through F or all together? All right, what do you got? Someone give me an answer. I'm hearing a chorus of A's and a chorus of it's the same. It's the same because it's in a series, right? That's our thought. All in a series, all the same current, therefore all the same brightness. That would be true if they were all the same bulb, same resistance, but they're not. Brightness, which I didn't explain to you until now, is power. Power is brightness. Think about it. That's what it means. If it's a light bulb has an amount of power. That means how much energy it releases every second. Brighter bulbs will release more energy every second. That's why they're brighter. So which bulb is it? A. A is the bright bulb. Not necessarily because it has a higher voltage, although in this case that's true, because they all have the same current, so more voltage is going to be more power. But look at power. Don't look just at current or just at voltage. Look at power. Power is going to tell you which one is brightest. It's the one that's dissipating the most amount of energy per time. All right. Parallel circuit. Many of you added this up and got 605, forgetting that the sum of the inverse of the resistances is the total resistance. So 1 over 80 plus 1 over 60 plus 1 over 75, et cetera, et cetera, et cetera, goes to 12.38. And then I know that I'm dropping 18 volts across the whole thing, so V over R is I, that's 1.45. In this case, however, is 1.45 amps going through every resistor? No, because it's in parallel. The current splits. But what stays the same? Voltage. It's 18 volts. It is not split evenly. Some people want to take 18 over 6 and get 3 and say, okay, if it's 18 volts, 3 volts goes to each of the 6 resistors. No, it's all 18. Because remember, voltage is a surface. If you go up to the top of a hill with your skis, and there's 6 runs, and you go down one, and your friend goes down the other, and you get to the bottom, you meet up, and you say, I went down the whole mountain, and the other person would be like, so did I. And you wouldn't think that was weird. Same thing here. Okay, 6 different runs, but we're all going down the same voltage. So it's all 18 volts for any given resistor. Every resistor gets 18 volts. Now I've got V and R, so I can get I by doing V over R, so that's these. All right, just V over R each time. And if I add all these currents up, I should get the total current, 1.45, which I do. I find power by doing V equals I times, or power equals V times I. Again, all 6 of these bulbs, if you add them all up, all their powers go up to 26.2 watts, because you can't drain more power in the total circuit than you're draining per bulb. Like on average, right, you have to drain the same amount of power each way that you look at it. Which bulb is brightest? They're not all the same. D is the brightest bulb because it's dropping the most joules per second. You with me? Okay, I'm going to skip those. Let's talk about this one. Is this series or parallel? Yeah, it's elements of both, which means it's not both, it's actually neither. Right? Because in a series, in a parallel circuit, right, like there I should have all of my high altitude, high voltage, and there's all my low voltage, and we should jump from one to the other. But right here in the middle, there's this other wire that jumps from here to here to here, which means that's not in parallel with all of the other resistors. The 6 and the 14 are not in parallel with each other, but they are in parallel with the 20. But the 20 is not in series with the 6 and the 14. It's neither. So the question is, how do you solve this thing? I'm just going to see if you can figure it out. I want you to solve for the current through and voltage dropped by each resistor in this circuit, each of the 3. Ready, go. So maybe most of us have not gotten there, which is fine. I gave this to you cold without talking to you about strategies for doing it. I wanted to see where we got. Guys, I do need your attention now. Let's take a look at maybe a way to solve this. There are multiple ways of solving this. We're going to look at 2, one today, one Friday. What I'm going to do is I'm going to take this circuit and I'm going to simplify it. I'm going to think about ways to make it easier to think about. What's the first way to make this circuit easier to think about? Well, I can't split the 14 and 6 up because they're not split up. But what I can do is look at the 14 and 6 together and say, if it were just the 14 and 6, what are they? It's a series. So what can I do with series? Series resistance, what can I do with it? Just add it up. So I could say, hey, this circuit is equal to that circuit. Right? Instead of a 14 and a 6, it's just a 20. Are you with me there? The battery doesn't know the difference here. And then I'm going to simplify it again. Because now I have just 2 20s, and how are they connected? They're in parallel. So I can just do 1 over 20 plus 1 over 20 is 0.05 plus 0.05 is 0.1. And 1 over 0.1 is 10. So it's 10 ohms. Fun fact, if you have exactly 2 identical resistors in parallel, their equivalent resistance is half of one of the 2 resistors. So a 20 and a 20 is a 10 in parallel. But it only works with 2. That's the only time that works. You don't get to do it with 3 or 4 or 5 or any other number. Just if there are 2 identical resistors, cut one of them in half, and that's your parallel resistance. Now I'm here. I can just say these 3 resistors, the 14, the 6, and the 20, to the battery are no different from just putting one 10 ohm resistor in there. Are you with me on that? That okay? Okay. What can I do with this circuit? Very simplified circuit. What can I do with it? I can find the math. I can find which quantity? I. I have V and R, I could find I. I do V over R, that's I, that's 1 amp. It's pushing an amp of current. Now that amp is true everywhere for every circuit because they're all the same circuit. The battery is pushing an amp of current. Now, what we're going to do is we're going to back up one step. I'm going to go back one step and say, well, it's not really a 10 ohm resistor, it's actually two 20s. If I split into a parallel branch, what stays the same? Voltage. How much voltage is dropped across the one 10 ohm resistor? 10 volts. So how much voltage is dropped across either 20 ohm resistor? 10 volts. Right? We keep that the same. So I can say, hey, 10 volts over 20 ohms is a half an amp. That must mean I have a half an amp through each 20 ohm resistor. Are you with me there? Okay. But it's not really a 20 ohm resistor on the inside track there. It's actually a 14 and a 6. So when I move back one step and I split that 20 into two resistors in series, what stays the same? Current. So I know it's still a half amp through each branch, but now it's a half amp through a 14 and then through a 6. A half times 14 is 7. A half times 6 is 3. And there's all my voltage. I've got 7 volts and a half amp through the top resistor, 3 volts and a half amp through the bottom, and then 10 volts and a half amp through the side. So to start it again from the top, I've got an amp of current coming out of the 10 volt source. It splits into two half amp branches, one that drops 7 and 3 volts for a total of 10, and the other that drops 10 volts for a total of 10, so that any way my electron goes, if it goes through the inside branch, that's 7 and 3, there goes 10, and it's a half amp this way, and it goes 10. Does current always split evenly? No, it doesn't. Why did current split evenly in this particular case? Same resistance on each branch, 20 ohms each time. You're going to split the current evenly. If you have big, small, most of the current goes with the which one's easier? The smaller resistor. Most of the current will go the small resistor way, the easier way to flow, and then a few electrons will go the other way. So it will split unevenly if the resistors are different size, such as in the next case, which we'll look at in a second. But there's a system to this. One, you simplify the thing to a single resistor. And may I suggest that, like I did, you redraw each simplification step. I really recommend that. You start with the original circuit. You have step A, which is the first simplification, step B, which is the second, step C, which is the third, and keep going until you have exactly one resistor, and you got its equivalent resistance. Find the current on that equivalent resistance, and then step backward to each next most complex circuit, solving. And every time your one resistor turns into a series, you keep the current from your previous one, and every time it turns into parallel, you keep your voltage from your last one. It's a nice, systematic way of solving literally, or almost literally, any resistor bundle, right, circuit. So this is kind of our system for doing this, which we're going to practice here with the next one, which is, harder. Are you ready? A few people still writing here. So, try this. So, here is my parallel circuit. I'm going to simplify it again, because this is two little parallel blobs in series with each other, as opposed to last time we had a series in parallel with another one. Right, so what I'm going to do is I'm going to take the 10 and the 40 on top and say those are in parallel with each other. So I have to go 1 over 10 plus 1 over 40 equals 1 over Req, and that becomes 8. And then I do the same thing with the bottom two, the 10 and the 50. 1 over 10 plus 1 over 50 equals 1 over Req, and that becomes 8.3. So the top two resistors turn into one 8 ohm resistor, and the bottom two turn into one 8.33 ohm resistor. We okay with that? Questions? Now, what is this? Simple series. I can just add them up and say, okay, that all just turns into 16.33. So one 16 and a third ohm resistor would do the job of those four, the 10, the 40, the 50, and the 10 added up in that way. The battery doesn't know the difference. From here, I can go backwards. I can say, well, 10 volts over 16.3 ohms is 0.61 amps. So I know it's 0.61 amps pushed by the battery every time. That just goes all the way back. That's the battery current. But I take one step back, and my 16.33 is actually two resistors in series. So what stays the same? Series is current. Okay, so it's still 0.61 amps, but it's through 8 and 8.3. That's 4.9 and 5.1 volts, respectively, right? So I say I times R and I times R gives me 4.9 and 5.1. When I add those two up, I get 10, which is the battery voltage, so I know I'm good there. So I know I've got 4.9 and 5.1 volts. But it's not really an 8 and an 8.3, is it? The 8 is actually a 10 and a 40. What stays the same when I split a 10 and a 40 out parallel? Voltage stays the same, so I know it's 4.9 volts on both sides of that branch, and I know it's 5.1 volts on the other side of that. So I've got voltage and resistance, and I just do V over R 4 times. 5.1 over 10 is 0.51 amps. 5.1 over 50 is 0.1 amps. And then up here, 4.9 over 40 is 0.12, and 4.9 over 10 is 0.49. You with me? Any questions about any of my math? Anything that I did that you're like, huh? Because I guarantee you, you will have to solve circuits like this and more complicated. Okay. So let's just do a big kind of review. I'm going to go back to the big circuit here. And we're going to say there's that 0.61 amps. And it's going to split 0.49 and 0.12. What's 0.49 plus 0.12? 0.61. Right? Because the current going in and the current coming out have to be the same. It's conservation of charge. You can't have more charge going out than coming in. That's impossible. Right? In the same way, the other way, you can't have more charge going in than coming out. It must be the same. So the 0.61 must be conserved between the two branches, which it is. This time not evenly, though. And then, let's see, 4.9 amps through 10 ohms is 4.9 volts. 0.12 amps times 40 ohms is also 4.9 volts. That makes sense, because it's parallel. Should drop the same. Then that current recombines to 0.61 for that little wire. But then it resplits 0.51 and 0.1, which when you add it up together is 0.61 again. Makes sense. And then 0.51 amps and 0.1 amp through 50 and 10 ohms, respectively, gives you 5.1 volts on either side. And then the current recombines to 0.61 amps again. So the current by the battery, that's the biggest current that there can be. You can't get more current somewhere else, because the current is either 0.61 or a split off of that, which means it's always at or less than 0.61. And the voltage must be less than 10 at all times. And any one trip that I take, I could start at the battery, go up and around, turn left, turn right, and that's 4.9 and 5.1 drop. That's 10 volts. Or left is 10 volts, or right or right left. They're all 10 volt loops. I can take any loop I want, and I take 10 volts to do it. So that makes sense. Like, we can't drop more voltage than we have. If you ever go through, like, if you ever trace your finger from the battery around through the circuit and back to the battery again, and you go through more than 10 volts of drop on a 10 volt battery, you did something wrong. You should be able to go through any direction. So there's lots to check here. Yes? Feeling okay? Now, they get more complicated, as you might imagine. We're not going to solve this one today. But I just want to talk to you about what's coming up. We have two ways of solving circuits. This is what we call, well, not this, but what we did is what we call circuit simplification. You take a circuit, you break it down to one single resistor, and then you make it more complicated on the way back, solving for stuff as you go. And that is one way of solving a circuit. In this case, we take the bottom two and add them together as a series. Then these three, add them in parallel, and then add them in series with the 6 ohm along the bottom. That's how you do it, right? Series, parallel, series. And then you just solve it and work backwards. You could do that. You can also do what's called Kirchhoff's laws. And Kirchhoff is this guy, a German dude, who did two awesome things in his life. One thing that he did was study what happens in circuits, and the other thing he did was study what happens if you get a hot gas cloud in space and shine light through it. And he came up with rules for both of them, and they're both called Kirchhoff's rules. Because you're either going to be doing circuits or astronomy, and you're probably not doing both at the same time. So when you say Kirchhoff's laws, everybody knows which one you're talking about based on the context. But in any case, Kirchhoff just says, let's not simplify it, but let's use conservation of energy. Where if I'm a single electron and I take a loop, I should lose as much energy as I gained in the battery. And then you set up a system of equations and do linear algebra. Remember reduced row echelon form? Hey, that's coming back. That's coming back. That's an exciting one. If you don't know what it is, it's just solving a system of equations. I will not make you do matrix, linear algebra and stuff, but if you can solve systems of equations, right, a plus b plus c equals 5, 2a plus 5c equals 7, and 3b plus 2c equals 10, if you can solve that system of equations using substitution and elimination, you're good to go. And that's Kirchhoff. But here's the deal, guys, is that you don't have to like both of them. There can be one that just clicks in your brain, and if that's it, do that one. I'm showing you two ways, and you need to know one or the other or both. And sometimes for given circuits, one is better than the other. There are some circuits that are so complex that breaking them down into a single resistor is actually really hard, and use Kirchhoff. And there's others where running Kirchhoff loops and solving a system of equations is just a lot of work, so you use circuit simplification. But technically, any circuit is solvable for both. So you just have to make sure that you, this is kind of a pick your poison. You get to pick the one that you like the best and use it to solve everything. And as long as you solve things correctly, I don't care if you do that. Although sometimes it will be much easier to do one rather than the other. And we'll take a look at some times when that's a thing.